Okay, so welcome back to another video. So in today's video we have a matrix exponential, which is that's very interesting. We have e to the power of a 2 by 2 matrix. It's symmetric. So we have the entries with 0, p, and 0, and then multiplied by t, and we're being asked to evaluate this matrix exponential. So how would you tackle this? Really, there's going to be some like power series representation, and then of course we're going to actually have to do a little bit of like matrix algebra. And now of course, to really start this off is that I'm going to use the power series representation for the exponential function. So we have that e and then to the power capital AT, and then capital A is just representing like it's representing a matrix. So of course we know that if power series representation is, so let's see, the index starts at 0, yeah, and then this is AT to the power n and then divided by n factorial. So that way we have that this is the infinite sum of some matrix capital A to the power n and then t to the n, and then divided by n factorial. We're given that we call this matrix A is equal to, so we have our entry 0, p, 0. Then we know that A to the power n is actually going to equal, there's actually some conditions that satisfy this. We have one matrix that this is going to be, so if I were to put just our standard matrix, so n, and then do the same thing over here, then we have the following. So we have that the first one we would have for the top one, we have p to the power n, 0, 0, p to the power n, and then this is if n is odd, or n is even, excuse me. This would be if n is even. And then the next one we would have is that we would have 0, p to the power n, p to the power n, and then 0. And that's if n is odd. We have two different matrix depending on our number for our index n. So what does this mean when we're trying to rewrite all this stuff out? Well, you'll see in just a sec. So now, so then we have e to the power, so let's see, 0, p, 0, then times t. Then if we write out the power series formula, so we get that this is, let's see, n is equal to 0. We have t to the power n, and then divided by n factorial. And of course we have our matrix 0, p, and then 0 to the power n. So what that means is that we actually have to consider both, for our index n, we have to consider both the odd and even terms. So that means we have to split this up into a sum of series. So we're gonna add up for the power series representations for ones dealing with the matrix when n is even, and then the same thing, add that up for when our terms are odd. Also that for n we're dealing with evens and odds, so we have to rewrite the terms into even and odd recursive formulas. So for this one we'll focus on the even integers, so I'll change this n to be even, so this will be 2 times n, then that'll be 2n factorial. And so now because we're dealing with even integers, that means this will be p to the 2n, 0, 0, p to the 2n. And now next I'll deal with the odd terms. So this is now we change this to 2n plus 1, and then 2n plus 1 factorial, and then we deal with our matrix. So this will be 0, p to the 2n plus 1, p to the 2n plus 1, and then 0, like so. Okay. And I'll also just write this such that over here this is our even, and this is our odd. So with that, so now we can actually perform some we can actually distribute the sums into each of the entries of our matrix. So then we have that, let's see, I think this box is big enough to fit in. Yeah, we're good. So now we distribute this infinite sum over here. So we have, so this is the infinite sum, n is equals 0 of, so we just multiply t to the power 2n, then p to the 2n, divided by 2n factorial. This will be 0, that will be 0, and then over here is infinite sum of the same thing, t to the power 2n, then p to the power 2n, divided by 2n factorial. And now we're going to add this with our, now distribute the infinite sum for now our odd terms. So then over here, this will be 0, then this will be the infinite sum, n is equals 0, t to the 2n plus 1, then p times p to the 2n plus 1, divided by 2n plus 1 factorial. Over here is the top right corner, that entry is going to be the same thing. The infinite sum, t to the 2n plus 1, then times p to the 2n plus 1, and then 2n plus 1 factorial. This will be 0. Now the last thing is now we want to know what are these infinite series, the power series are equal to. What will it represent? So we actually know that. So power series below, I'll say that's just supposed to be no s. Power series. So we know that the infinite sum, t to the power 2n, then p times p to the power 2n, and divided by 2n factorial, that actually, that power series is supposed to represent the hyperbolic cosine of p times t. And then the other one is that if we're dealing with the odd terms, so t to the 2n plus 1, then times p to the 2n plus 1, divided by 2n plus 1 factorial, the representation is that this is actually just equal to the hyperbolic sine of p times t. So this would mean that we have that, let's draw this in black. So then if we set everything together, then we have that this would be, over here, that will be hyperbolic cosine of pt. That'll be 0, 0, hyperbolic cosine pt. And then we add this with the odd, with the series representation. This is hyperbolic sine of pt, hyperbolic sine pt, then 0. And so therefore we do some matrix algebra. We just add the two matrices together. We get that this is hyperbolic cosine pt, that's the top left corner. Bottom left corner, this is hyperbolic sine of pt. And top right corner, hyperbolic sine pt. And then bottom right corner, hyperbolic cosine pt. And there we have it. That is our final evaluation over here, denoted in this black box. All right, and we are done. Now that's pretty cool if you ask me.